Our first chapter in math155 is on the counting systems commonly used by computers, binary, octal, and hexadecimal. But let's first start off by reviewing the decimal system, the counting system commonly used by humans. The decimal system is also known as base 10, and if you think about why, that's because we have 10 fingers. It's true that there have been other counting systems used by humans. The Babylonians, for example, did like bases that were evenly divisible by 3, but in this day and age, we've pretty much settled on the decimal system everywhere. So if you take a look at counting in the decimal system, starting from the number 0, adding 1 each time, we get 2, 3, 4, 5, 6, 7, 8, 9. And then when we want to write the number 10, note that in base 10 we use 2 symbols for the number 10. We don't have a single digit or symbol to represent that number. So what we do is we write a 0 in the column, and then we add 1 to the column on the left, saying that we have one complete set of 10 with nothing left over. So once again, noting that we don't have a single digit or symbol for 10, we actually need 2 symbols. And the reason we're going into such detail here is because these ideas are exactly the same when we're using different bases like binary or octal or hexadecimal. So the number 23 in base 10 means 2 full sets of the base 10 plus 3 left over. What about the number 123 in the decimal system? Well, the number 1 is in the hundreds place. What that means is that instead of having just a set of 10, it's a set of 10 by 10. In other words, a square with 10 on each side, or 100 bits inside it. Plus 2 sets of 10, plus 3 left over for 123. And the reason we went into such great detail, as I said before, is that for bases other than 10, we use exactly the same idea. No single digit represents the base. Instead, we set that last column to 0 and add 1 to the column to the left. For example, let's take a look at base 4. Base 4 is not actually a base used by computers, but it's a nice useful example because the base isn't too big and it will give us all of the ideas that we need. And although base 2 is even smaller, it gets a little confusing. We've got lots of zeros and ones flying around. So let's start with base 4 as our first example. Counting in base 4, we start with the number 0, and then we keep on adding 1 to get 1, 2, and 3. And then when you feel your mouth starting to say the word 4, instead, because we don't have in base 4 a single symbol, we write a 0 in our last column, and we add 1 to the column on the left. And so that number there is 4 in base 4. Now, if all of this seem a little bit abstract, then a fun and silly way to think about it, but it turns out to be quite memorable way, is to think of base 4 as base dog. Why, you say? Because dogs have 4 paws. For English as a second language people, a paw is what you call the foot of a dog. So in order to count in base dog, our number 0 means that we have no paws, we have 1 paw, 2 paws, 3 paws, and then the number 1 in the next column means we have a complete dog for a set of 4 paws with none left over. Continuing to count then, we have 1, 1, so 1 dog, 1 paw, 1 dog, 2 paws, 1 dog, 3 paws. In other words, 1, 3 base 4 is 1 dog plus 3 paws for a total of 7 paws, and then 2, 0 is 2 complete dogs or 8 paws. Continuing onward, we get all the way down to 3, 0, 3 dogs, no paws for 12 paws, 3, 1, 3, 2, 3, 3, and then the question becomes, how do you actually write that? You add a 3, when you add 1 to 3, you get 4. We write 4 by writing a 0. We add 1 to the next column. 3 plus 1 is 4, so we write a 0 and then add 1, and then this number 1 dog of dogs, that's the same as 4 dogs, which we know to have 16 paws. And that is it's not a coincidence that that number is 4 squared. So the number 123 base 4, that subscript that you can see here, that 4 means that that's actually the base. Normally we leave that off if we're counting in base 10, but we add it the moment we have a different base so people don't get confused. So that number, 123 base 4, is, so 1 complete set of 4 times 4 of 16, plus 2 complete sets of 4, which is 8, plus 3 left over. So 1 times 16, plus 2 times 4, plus 3, and that is equal to 27. So let's just do one last example in this lesson, which is converting the number 201 in base 4 to decimal, remembering that the 4 in the subscript is the base, and we write that the moment that we're using a base that's not base 10. So a nice straightforward way to do this is to write the 3 numbers out like so, the 2, the 0, and the 1, and then we fill in those spaces with what those numbers represent. The number to the right, the 1, is in the 1's place. The second number over, the 0, is in the 4's place. And the third one, from the right, the 2, is in the 16's place. So if you think about the decimal system, it would be the 1's place, the 10's place, and the 100's place. Here we've got the 1's place, the 4's place, and the 16's place. So 2 times 4 squared is 2 times 16, plus 0, plus 1, gives us a total of 33 in base 10. We'll be doing more examples in class next time, and thank you for watching this video.